I dot is 0. So, this term will be 0, theta I dot term will be 0. Now, this will be 0. So, this is gone. Okay. So, what we will end up with T I is equal to B I j T j, and if you look at this expression, it is nothing but a single rigid body, the velocity transformation expression. So, that means, suppose for my this hand, if you know the velocity of this point, and if I ask you what is the velocity of this point, no, this is nothing but velocity of that previous point plus omega into omega cross this distance, right, and that is the expression which will come here. Okay. But now, since there is a joint is there, so there is a joint is there. So, that joint has to apply some motion. So, that is the motion theta I dot is applied, and then you get this T I. So, now this is between I and j. So, P I we call it a twist generator, that means it is providing extra motion. So, we call it a twist generator. Okay. And it has some interesting properties, that I j and j k will give rise to I k because of the serial connectivity of the links there. So, again we put them in a bigger matrix vector form. This T left hand side, this T contains the twists of all n bodies, and theta dot it contains all the joint rates, and this n is our the same old NOC, is the natural orthogonal complement. And now, this n we were able to write in a block matrices forms. The first one in L, the L stands for lower, it looks like a lower triangular matrix, but please note all of them are the block matrices. This one is actually 6 by 6 identity matrix, B21 is 6 by 6 matrix, and that way the all components here are the matrices. So, we call such matrices block lower triangular. Here it looks like a diagonal matrix, but again the diagonal elements are not a scalar element, these are the 6 dimensional vectors. So, we call it a block diagonal element. Okay. So, again the story is same. So, we pre-multiply n transpose to the 6 n equations of motion, and in the right hand side the total forces and moments which are hiding inside these ranges consist of external forces and moments and the constrained forces and moments. Now, as we know, the reaction forces do not do any work. Actually, this n transpose W c which I showed earlier here, that I transpose this j is equal to 0, it comes from the fact also that reaction moments do not produce any work. What that matter? So, power is also 0. So, from that concept, if we pre-multiply with n transpose, we can show that n transpose W c will be 0. So, we will end up with a set of equations which can be represented by I theta double dot plus C theta dot equal to tau, where these equations are called Euler-Lagrange equations of motions. Okay. And here you can note that we have not done any partial differentiation here. So, what we did is we used the knowledge of mechanics and you use a little bit of linear algebra concepts to bring to the equations of motions which are minimum set. So, for 6 degrees of freedom robot it will be the 6 scalar equations here, and then correspondingly we give a name to all these matrices and vectors. I is n by n generalized inertia matrix, because we are talking about the whole system now. So, for 6 degrees of freedom robot it will be 6 by 6. Capital C we call matrix of convective inertia terms, because it will have theta and theta dot terms, and that terms will be multiplied theta dot. So, that will be square terms of theta dot. If you have studied about Coriolis acceleration, the centrifugal acceleration, centripetal acceleration. So, those are the terms are contributed from C. So, these are called in generic manner convective inertia terms. The tau is the n dimensional vector of generalized forces due to driving torques and forces. Okay. Also, if there is any gravity you want to consider, so that should be included here. If there is some dissipation forces due to frictions on the joints, or there is some other environment force, any other things which you have not considered so far can be put inside the tau. These portions it is for the completeness sake, you can slowly study when you are at home, that I can be written as n d transpose m tilde n d, whereas m tilde is equal to n l transpose m n l. Now, this I am showing it to emphasize the point that I do not want to use the computer yet. So far many people may do it, okay, I have the expression of n here. Now, let us use the computer and start multiplying it, and then I get the numerical results. But my intention is not to get the numerical results immediately, because I would like to study more about it. Okay. I do not want to see behavior for one time, just like if you meet a friend for meet a person first time, he may be very nicely talking to you, you say very nice, but maybe he is very rude and rough otherwise, right. So, here the same thing, if you see one time numerical results, you may not get the complete picture. So, we want to get the analytical expression, that what are those elements inside. So, with that intention, that IIJ, that means the GIM, the generalized inertia matrix, if I look at the elements, the 1 element, 1 2 element, 1 3 element, they can be very nicely expressed as a combination of vector matrix multiplications. And inside this tilde matrix which is sitting here, we call it composite mass matrix, can be actually calculated recursively by knowing the previous information, right. Now, details will take little time for you, just try to get the physics at this moment, and if you are interested to know this numerical. So, there are some numerical example in the book, but I will show you 1 degree of freedom and 2 degree of freedom to get you some feeling. So, the next one is the vector of convective inertia H is equal to c theta dot. Again you can see this small w tilde prime can be computed recursively knowing the previous one, and the tau the torque similarly knowing the previous one. So, now come to an example and see that if I have to apply the same methodology, how do we do about it. So, for one link system, this generalized inertia matrix will be of what size? 1 by 1, that means a scalar term, right. And this term will look like P transpose m tilde P, since there is only one body, tilde concept will not come here, actually m tilde will be just simple m, and if I expand it. So, I did the expansion here, E transpose I E plus m E cross D transpose E cross D, that is the expression it will come. Okay. Let us do it for you, so that things are little clear. So, this I the scalar component is equal to P transpose m P, as I told you this is nothing but m. So, what is P transpose? P transpose will be E transpose E cross D transpose, m has I 0 0 m into 1 E cross. Okay. So, let us do this operation first. So, I into E I E plus 0 into this thing, since it is a 0 matrix nothing will come. We come to bottom 0 into E 0 and m E cross D. Now, we do this operation here and the final result will be E transpose I E. So, E transpose I E plus m into transpose E cross D. Now, at this junction I wanted to use the numerical values of it, okay. But before that let me see, without using numerical values can I simplify it further. This portion can be easily seen that this is in the form of A cross B transpose C cross D. Actually transpose for Cartesian vector 3 dimensional vector actually means a dot product. So, A cross B dot C cross D. If you go back to your first year algebraic course, now this can be written in a simplified form A dot C into B dot D minus A dot D into B dot C. Okay. So, A dot C, B dot D, and then A dot D into B dot C. If you apply this formula, then my expression will be very simple. So, let us come from here. So, E transpose E, A dot C means E transpose C. So, this will be identity, and then D transpose D. Now, D transpose B means D dot D. So, a vector dot product of the same vector means what? Its magnitude square, right. So, this will be basically D square minus E dot D. Now, look at here, for single link system. So, if this is my single link, D is along these directions, E is along the perpendicular, because that is the axis of rotations, right. So, E and D are always perpendicular, orthogonal. So, then what will be the result? E dot D will be 0. So, this is 0. So, this term simply giving rise to m into d square. So, without doing any numerical computation whatsoever, I know that this will be simple m d square. Is it not beautiful? So, that is the reason we did not wanted to do the numerical computations immediately. So, but still in this example on this slide, I wanted to do it numerically. E is a unit vector which is indicating the axis of rotation of this revolute joint. I use this fixed frame, which I call it a first frame, I indicate with the square brackets. So, it will have 0 0 1 component. D is this component from O to C, half of A cos theta. I am assuming that C is at the half of the link length. So, A by 2 cos theta, A by 2 sin theta. So, this is cos theta here and sin theta direction, and Z component is 0. The I is the inertia tensor for this rigid link. Now, for the slender rod, now I can neglect the IXX component here, because it is a thin rod, but YYZZ component will be appearing here. So, since about mass center it is m square by 12. So, IYY will be m square by 12, IZZ will be m square by 12, and the diagonal terms off diagonal terms are 0, because this I am doing it with respect to a frame which are indicating the principal axis. Q is the rotation matrix. Now, why I need to use the Q? In this planar case it will be very simple, not required, but in order to complete the method. So, I have chosen a frame 2 here, but all my calculation I wanted to do it in frame 1, because I have chosen E in frame 1 and D in frame 1. So, I need to convert it, the I represented in 2 I wanted to convert into 1, and for that the transformation formula is Q, the rotation matrix, multiplied by this representation and the Q transpose. For vector transformation it is the Q into the vector only, but for matrix transformation it is Q matrix Q transpose, and that is the expression I have shown it here. And now, if you form that P and M, if you put everything in these values, you will get nothing but 1 over 3 m square. Let me complete this job on this paper also. So, we have seen that M E cross D transpose E cross D. So, we have E transpose I E plus M E D transpose E cross D. So, this we got it as a D square, and if I am considering D is at the half of the link length, that means if this is my link length A, if this is at half, if D is half, so then D square will be A square by 4. Then I E, now E has component 0 0 1. So, whatever may be the matrix here without actually knowing it. In my slide I have shown you the values. The final result will be, I mean this result will be the third column, and when I pre-multiply with E transpose 0 0 1, actually my final result will be this one. So, E transpose I E is nothing but the Z Z component. And what is Z Z component in my previous slide? It is m square by 12. Okay. Now, you add it, m square by 12 plus m square by 4 is equal to by. What does it mean? M square by 3, if you remember, m square by 3 is nothing but the moment of inertia of a slender rod about its end, that means this point. Okay. Now, because the body is rotating about this point. So, if I have to write the equation of motion from the rotational equation of motion, that means the inertia into angular acceleration should be is equal to the torque applied on it. So, then moment of inertia about this point should be calculated, which is m square by 3. So, in our formulation it is coming through a set of equations which have formed and the computation which have performed. Okay. So, this inertia matrix, or in this case is a scalar, is m square by 3. Now, the h component if you calculate, it will give you 0, because it will not lead to any square term. Okay. And that is obvious from this expression also. Now, E cross E, a vector cross product with this vector is 0, right, multiplied with I 0, no, E transpose multiplication it will be 0. So, the first term will lead to 0. Now, the second term E cross I E, let us see I E is a some vector, it will produce some vector. So, E cross some vector will be a vector perpendicular to E, E cross V will be like E cross V. So, this is E direction and this is V direction. So, E cross V will be perpendicular to E, and now on the left hand side I have a E transpose. So, E transpose a vector which is perpendicular to E, which will be 0. So, without doing any computation whatsoever, now we see this term is 0, this term is 0. So, final result is 0. So, no computation is actually required if you have the expressions available to you. Now, similarly tau 1, that means the only generalized force we have it, if you express it, now it will come like tau minus half m g a sin theta. So, the final equation of motion will look like 1 over 3 m square theta double dot is equal to tau minus half m g a sin theta. Is it not the same rotational equation of motion if you try yourself, that the moment of inertia about the axis of rotation multiplied by the acceleration is equal to the force, the external force applied by u maybe, and the minus in this case the gravitational torque. Okay. So, in case of recursive algorithm, no, the steps are as follows. Now, first you calculate the velocities and the acceleration in the forward recursion, and in the reverse recursion you calculate what we call the inertia forces, in this case inertia ranges, and you project on the axis of rotation to give you the joint torques. Okay. So, this is the whole algorithm, and in the next class we will use a software to see that how the numerical analysis results can be generated, followed by a two link example which is little more complex, but I would expect you to understand what is been told today. If you have a quick questions, you can ask me, otherwise we will stop. Yes.
Both transforms theta dot to twist.
Which n and j?
J is Jacobian.
They are some way similar, but not exactly actually, because the angular velocity will not be a directly partial differentiation of some coordinates. So, because of the angular velocity component, no, they are not exactly true in mathematical sense, but people loosely use this term Jacobian, but this Jacobian is different than the robot Jacobian, because in robot Jacobian what we do, the end effector of the twist of the end effector, that in this point we correlate with the joint rates, but in this case what I am doing is the velocities of these mass centers of all the bodies I am correlating with the joint velocity. So, there is a relations between them, but this n and that j is not same. Yeah.
Is this Euler equation multiplied by denote
Yeah.
giving you
Euler-Lagrange. Euler-Lagrange equation. Yeah.
So, why it is Euler-Lagrange only? It could be called as D-Lambert.
Yes, because it is popularly known Euler-Lagrange. So, to convey this correlation, so we say it is Euler-Lagrange. Yeah, it could be any, for that matter it should be called as a constrained equation of motions, which has a minimum set, minimum constrained equation. Okay, so thank you and see you tomorrow at 8 o'clock again.